Hi guys, in this video we're going to look at a worked example titration calculation involving a dilution and identification of an unknown hydroxide. So the question says 1.75 grams of an unknown hydroxide, XOH2, was dissolved in water and the solution made up to 250 centimeters cubed exactly in a volumetric flask. Now a volumetric flask, it's that tall one with the long thin neck that's used for inverting and making solutions. In a titration, 25 of this solution, so 25 mils was taken out of this solution and titrated against the acid. So anyway, 25 mils of this solution required 20.25 centimeters cubed of 0.3 molar acid to reach the end point. The end point is when the colour changes. And we have to identify X. So there's about 6 steps, ice creams, depending how you identify a step in this calculation. So the first thing we have to do in any question like this is to write out the balanced equation. So we're doing the titration between an acid and here's our alkali. So we write the acid plus the alkali. And this always gives a salt plus water. If you're not sure how to get the formula of the salt and how you know what goes where, please watch my video called What's the Salt? And we do lots of examples there. Now, if you look at the numbers and what information we're given in the question, there's only one thing that we can do next. We don't have enough information on anything else to do anything else just yet. So we're given both a concentration and a volume of the acid, so we can work out moles of the acid. And remember to divide your volume by 1,000 to convert it into decimeters cubed, because the units of concentration are moles per decimeter cubed and we need to keep our units consistent. So we end up with this number for moles of acid. Then the third step, we look at the balanced equation. Now, these ratios, so the big balancing numbers in front, we've got a 2 there, we've got a 1 there. We don't write 1, so it's called stoichiometry. And we're going to use these ratios, these balancing numbers, to figure out the moles of this hydroxide. So you can see we've got twice as much of the acid compared to the hydroxide. So that must mean that moles of the hydroxide is moles of acid divided by 2. So here we are. Now these are the moles of the hydroxide in 250 ml. So remember the question says we made the solution up to 250 to begin with, then we took out 25 centimeter cubed portions of this. 1 centimeter cubed equals 1 mil, by the way, it's the same. So how do we get from moles in 250 to moles in 25 mils? We actually times by 10. So we do the moles in 250 times by 10 to get a slightly bigger number, and that is the moles in 25 mils. Because it's still the same amount of stuff, but you can think of it, it's in a smaller volume, so that makes sense. And then we're nearly at the end now, we're getting there. So now what do? We've got our moles in the 25 mils. We work out the relative molecular mass of this hydroxide now that we've got the moles. So we do the mass we're given in the question, 1.75 grams, divided by the moles that we've just worked out, and we get 58. So that number includes the X, and we don't know what the X is yet. To find the X, we do the molecular mass, relative molecular mass, that we've just worked out, take away the relative molecular mass of 2 OHs, and this will tell us the mass number of X and allow us to identify that metal. So if you look at a periodic table, I've forgotten to bring mine for this video, but oxygen's 16, hydrogen's 1, so 17 times 2 is 34. So 58 minus 34, that gives us 24. We look at our periodic table and we find the element with a mass number, a big number of 24. And if you look at the formula, that gives you a hint that it's got to be a group 2 metal to have that formula. And it is indeed, it's magnesium.